Section 4.4 is the last section we're going to cover in Chapter 4. The next thing that we're going to do is actually going to be in Chapter 5, and we're going to change gears significantly, okay? Everything that we've done in 4.4 goes back to derivatives and how we can use them. Basically, looking for locations where we have the greatest increase or the greatest decrease of something happening. So in this section, what we're looking for is we're looking for the location where things find us at the greatest rate of change, where things are increasing the most rapidly or decreasing the most rapidly. That's what we're going to be looking for. Now, in particular, this is related to the idea of something called inflection points. And inflection points brings us into second derivatives. So let's just talk about second derivatives today, and then we'll continue with the idea of inflection points next time. So start with a second derivative. A second derivative is a derivative of the derivative. Find the derivative, and then you take the derivative again. It's just the secondary process of taking derivatives. If you have the function y equals f of x, there's a couple of notations for derivative. You know the first derivative notation looks like y prime, right? This is the first derivative. And if you do the second derivative, it would be y double prime. Okay? That's probably everybody's favorite notation, and that's wonderful, and we'll use it probably the majority of the time. But you should be aware that there's another notation that could be used so that when you see it, you know what it's talking about. The other notation is akin to what we were looking at in Hannah's calculator when she was finding in deriv. Do you remember it put a d on top and a dx on bottom? Well, in particular, the first derivative usually looks like dy dx. Do you remember that notation? We don't use it very much, but it has a really nice feel to it because it looks like slope, the change in y over the change in x. So for second derivative, it looks like this. Okay, make sure you put the 2's in the right places. It's a d, it's a subscript, didn't mean sub, superscript of 2, y. And then on the bottom, it's a d and an x and the superscript of 2 after the x. They're in different locations. So I want to show you how we read that, because this is the proper notation. This is read as the second derivative of y with respect to x twice. And I know that feels sort of weird and funny, and part of that reason is because you're not going to go far enough in calculus or even in this particular textbook to see that you don't always have to take the derivative with respect to x. There are other things you can take the derivative with respect to. And that's why the notation looks a little bit funny, is because you're not going to get far enough along in this semester in calculus to see a different notation. So this is what it looks like. Okay? So let's do 2 examples real quick. They're not difficult, of finding second derivatives. Now here's the catch. If you're having to find a second derivative, what do you have to find first? The first derivative. All right? So make sure you're being careful when you find the first derivative so then you can actually find the second derivative correctly. So here's our first derivative. So we're going to do f prime of x. 32x cubed, so we're going to bring the 3 down. What's 3 times 32?
Oh, 3.
Yeah. 96. 96x squared minus 2.1 times the exponent 2. So 2.1 times 2 would be 4.2x plus the derivative of 7x is 7. Fantastic. Second derivative now. We are going to take the derivative of the derivative. So now I need to do the 96 times the 2 as the exponent. So what's 96 times 2?
192.
192 is right. 192x minus, what's the derivative of 4.2x? 4.2. And then what's the derivative of the 7? 0. And you're done. That's not so bad, right? Not so bad. Let's take a look at another one. This one's a little different because it's not a polynomial. All right, so g prime of x. What is the derivative of 3.2 natural log x? Yeah, it's 3.2 because it's a constant multiplier. The derivative of natural log x is 1 over x, so you can write 3.2 over x. What's the derivative of the 7.1? 0. Now, on your gateway, and in most of your homework as well, we've kind of said you don't really need to worry too much about simplifying, and that's a true statement. However, when you're going to take the derivative again, sometimes it's easier to rewrite it in a different way. So in this one, it's probably going to be easier for you to see this written like this to do the next derivative, right? So when there's an occasion to rewrite, and you need to see it a different way, do it. Just rewrite it a different way before you continue. So now you're ready to do the second derivative. So we have 3.2 x to the negative 1. So the negative 1 will come down, making that negative 3.2 x to what power? To the negative 2. Okay? And that's where we're going to stop for today.